Alright, so we're going to get into part 4 of this review now. There's 5 parts. I believe the next one should be Doppler. And Doppler and bioeffects finish out the review. This is going to be a rather long lecture, so be prepared for that. Take breaks as you need to. And we're going to be covering a lot of material here. So the early ultrasound imaging consisted of single image static scans. We called this the B scanners, which I suppose is where B mode today comes from. But the B scanners created single grayscale images and nothing moved in it. This was not real time. So if you're scanning today, this is very similar to any kind of panoramic scanning you may be trying to do now. This is what it was. You'd take a probe and you would hold it on the belly and slide the probe down in order to create the image. And so there was no real time. It just was a matter of sliding the probe over the patient's abdomen or other part of their body in order to obtain image of the structures. And motion in that case, because we had no real time, if you wanted to show anything moving, you had to use M mode. And so that's where the M mode scans came from. Of course, today we have real-time scanning, which allows us to see structures as we're sweeping through them. So it's a lot different. Everything looks like more of a moving picture as you're scanning. Of course, once you freeze the image, they look very similar. But the real time comes with something called a frame rate. So we have to, it's not going to feel like real time if we're getting 2 frames every 5 minutes, or more like the static scanners before. You got 1 frame for however long it took you to slide your probe over the abdomen. So frame rate is really what makes real-time real-time imaging occur. And so the frame rate is the ability of the system to create numerous frames each second, and we call this the temporal resolution. Okay, so it's how much it looks like real time is how closely our temporal resolution is to actually displaying things as they happen. So you could think of temporal resolution as accuracy in time, and a good temporal resolution has at least 20 frames per second. So if we get down below 15 frames per second, we're thinking, okay, that's not real time anymore. It starts to becoming a little jaggedy. So anything above 20 is considered real time, and below 15 you're getting a little laggy, and that's not good temporal resolution. So you have to know what the frame rate is, and you have to know all the things that affect the frame rate. And that's probably a good portion of the SPI exam, is understanding what's affecting your frame rate. So frame time versus frame rate. Frame rate is simply how many frames per second we can display on our monitor. Frame time, of course, is the same as the frame period, and it's the reciprocal of the frame rate. So things that affect the frame rate are the depth, of course. If it's shallow, you can have a very short return time on your ultrasound pulses, and you can create many lines of imaging quickly. But if it's deep, you have to wait for the sound to return, so that's going to take a lot longer. The number of transmit pulses in each line or picture is going to affect the frame rate, of course, because if we have to send out 4 or 8 pulses for each line, it's going to be much slower than if we only had to send out 1. And it should make sense that the line density is also something that affects the frame rate, because how many lines per inch you have, if you have 1 line per inch, you can do it with 1 scan, 1 pulse. If you have 100 lines per inch, then you have to do 100. So those are things that affect the frame rate. So when we look at how many pulses per image there are, each pulse that, as many pulses as is needed to create a line creates the line time, and then you multiply the line time times the number of lines in your frame, and that gives you your frame time. And so whatever your frame time is, you can just take the reciprocal of it, and that's your frame rate. So when we put multiple foci on our image, we get a slower frame rate, because multiple foci, of course, require multiple pulses in order to create them. So that's going to result in a slower frame rate. But as you know, multiple pulses and better foci results in improved lateral resolution. And so we can get better image quality by adjusting how many foci we're using. And along with line density, another factor in frame time is the size of the image. And of course, a small sector size can be scanned much quicker than a large sector size. And so we have the analogy of, a large football field takes longer to mow than a short little backyard, though the guys let the grass grow much longer in his little backyard. So the bigger the sector size, of course, the slower the frame rate. And as I said, line density, the number of lines per inch is going to change your frame rate. If you have more lines per inch, you get better lateral resolution, because we're insonating side to side more often, but you get a slower frame rate. So temporal resolution and image quality, we always want good image quality, but almost anything we do to improve image quality is going to decrease the temporal resolution. So increased quality is almost always equal to decreased frame rate. So there's always a trade-off between quality and frame rate, or quality and temporal resolution. Let's talk about pulsed echo imaging. So pulsed echo imaging is the imaging that we do with our ultrasound machines in order to create an image. We have 2 major components of the ultrasound machine to create pulsed echo imaging. I guess this is pulse echo instrumentation. One part of the system creates the sound pulses, and the other part receives the reflections back from the body. So we have the transmission of sound signals. A signal is sent to the transducer, which creates the sound beam, and then we get echoes back, which then are sent from the transducer into the system, into the receiver of the system. And this results in our diagnostic information. So our basic ultrasound system components are, of course, the transducer, the part of the machine that creates the ultrasound pulse. It's known as the pulsar, or the beamformer, or in some cases the transmitter. So those are all terms for the thing that creates the electrical signal initially. When the sound goes into the body, it creates echoes that come back to the transducer, and those echoes are then sent to the receiver. And the receiver is what processes those echoes for the display and storage of them. And this is all controlled by part of the machine called the master synchronizer. If you're thinking of a computer system, the master synchronizer would be the central processing unit. So the transducer, of course, is responsible for the transmission of the sound, where it transforms the electrical energy from the transmitter or pulsar into sound. And then it's also responsible for the reception of echoes, at which it converts the sound energy into electrical energy. All of this is started at the pulsar, or the beamformer, or the transmitter. So there's no industry-wide standard for any of these terms that I'm going to give you, so you're going to have to learn several terms for each component. We've already discussed how everything in ultrasound has multiple names. Well, this is where it really becomes important to know those, is when we start talking about the different components, because one manufacturer may say, well, that's the beamformer and it's responsible for only shaping the beam, and the other one may say, well, no, the beamformer is also responsible for apodization and voltage strength, and a third one will say, well, none of that's true, it's all the pulsar. Well, it's all true for all of them. Okay, so pulsar voltage terms that we hear, what it's creating. We hear the term output gain, that's the strength of the output, acoustic power, pulsar power, energy output, transmitter power, or just simply power. These are all synonyms. They all mean the exact same thing. The confusing part is when they start saying output gain or acoustic gain, because these are terms that gain is used for amplification, and we usually like to reserve amplification for the signal that comes back from the patient. But some people call the output, the strength of the output gain. So just be aware of that. If you see output gain, or you see transmitter gain or acoustic gain, then they're talking about the output power that's being created by the pulsar. So the pulsar is absolutely adjustable by the sonographer. We're required to follow the Alera principle, as low as reasonably acceptable, and so therefore we have to have a button on our machines in order to adjust the amount of strength that the pulsar is creating. Changes to the power will affect the entire image. Not only that, but changes to the power also affect have an effect on bioeffects and the heating of the tissues to the patient. We always want to minimize patient exposure, and that means we always, if we can, turn down the voltages, the output power, to a minimal amount. This is going to minimize the likelihood of any bioeffects. So in general, you always want to use less power and more receive gain if possible. So the pulsar creates the electrical signals that excite the crystal, and this occurs during transmission. The pulsar is responsible for the transducer output, and it's adjustable by the sonographer. Voltages created by the pulsar range from almost 0 up to approximately 100 volts. So that's a dynamic range of about 40 decibels. This, of course, varies with the system that you're using. Any change that you make to the pulsar, or output power, is going to affect the entire image. Brightness can also be modified by the receive gain, but remember, any change to the pulsar affects the entire image. Penetration results from having stronger signals that can penetrate farther, and so on large people we have to turn up the power in order to make this happen. The beamformer or pulsar determines the sound wave strength, the phasing, the pulse repetition period, and therefore the pulse repetition frequency. Of a side note, the pulse repetition period, of course, determines the depth of view. The shorter our pulse repetition period, the shallower our image. The longer the pulse repetition period, the deeper our image. And of course, because we have a depth button, this is adjustable by the sonographer. The beamformer is the part of the transmitter or pulsar that creates the beam signal that goes to the transducer. Some manufacturers consider this part of the transmitter, others consider it separate. If you're considering it separate, what you would say is that it receives the pulse from the transmitter, it creates the delays used in phasing, it creates the apodization signals, which helps of course reduce low-bar effects, it controls the dynamic aperture or the wideness of the crystal, and it sends the signal off to the transducer. So the beamformer is responsible for steering and phase transducers, and it's also responsible for focusing of phase transducers. A digital beamformer creates the signals in a digital form. Advantages of a digital beamformer are that it allows for easier system updates, it's extremely stable, and it's quite versatile. These digital beamformers are capable of a wide range of transducers, a wide range of frequencies. Pretty much everything in use today utilizes a digital beamformer. These are much better systems than the old ones. Once the signal comes back to the transducer and is sent back into the ultrasound system, it goes directly to the receiver. The receiver transforms electrical signals from the transducer into a signal for display, and it does this through 5 different functions that we were going to consider for it. There's actually 6 functions, but we're going to talk about 5 of them. Along with demodulation, there's another function that goes with that, and we'll kind of mention it. But the 5 that you need to remember are amplification, compensation, compression, demodulation, and rejection. So after the receiver completes its functions, what remains of the signal that came back to the transducer is simply the A-mode scan. So we've already discussed what an A-mode scan is. That is the scan that represents one line of pulse scan information. And so this is where it is created, is in the receiver at the end of the rejection. We have the A mode. After the receiver, the information is sent to a scan converter where it is processed for display, and then onto the display, which is typically a flat screen monitor today. There's several other formats that it could be, but this is the most typical in today's systems. We'll talk a little bit about flat screen monitors in a bit here. After we display it, we need to store it somehow. And so storage is what archives the ultrasound study and keeps a record of what we've done for the day. There's various types of storage: hard drives, also CDs, DVDs, videotape. Less useful nowadays is the magneto-optical discs, paper printout, photographs, or even sticking it on a USB drive. Those aren't typically done in the normal workflow. Normal workflow, we just send it to the hard drive, and from there it goes off to PACS. We'll talk about PACS in a minute. Controlling all of this, synchronizing all the different functions is the system computer. This maintains and organizes the timing and interaction of all the system components. Now that we've introduced all the components of a typical ultrasound system to you, let's go back and look at them in a little more depth. The beamformer, or as I said, the digital beamformer, creates the signal that goes to the transducer. Today we're able to have a special type of pulse created known as a binary encoded pulse. These binary encoded transmit signals have information in them that you could consider as binary information describing, you could call it a serial number of what that pulse is. These are also known as chirp frequencies and is also known as a type of Golay coding. We don't have to get into the various differences between binary encoded transmission, chirp frequencies, and Golay coding because they do the same thing. They all allow discrimination of return signals. There are some minor differences, but they're not very important. At the end of the day, what happens is any pulse that we send out using a binary encoded transmission has a code associated with it, so that if echoes come back to our transducer that don't have the correct code, we can throw those away because we know that they're noise. This allows us to improve our signal to noise ratio, and that's particularly good because we're not having to raise the signal, turn up the output power. We can just simply lower the noise by utilizing a binary encoded transmission. It's a really good thing. As you know, that the signal goes to the transducer and then creates sound which goes into the body, and then we receive signal back from the body, or receive echoes back from the body, which is turned into an electrical signal which is processed by the receiver. We have to have a switch between the receiver and the transmitter, because if we don't have a switch, then that powerful signal that's coming from the transmitter would also go to the receiver and blow its circuits out. So the switch is a very important part of the ultrasound system that protects the sensitive receiver components from the very powerful signals from the pulsar. You could just think of the switch as it switches the transducer between output mode and receive mode. It allows the correct signals to go out when they're needed. With each transducer element, you have a channel that goes to it. When I say a channel, I mean this is a wire, an element, beamformer circuits, and receive system circuits that are all associated with each little crystal element in the transducer. So most systems will have somewhere between 32 and 512 channels, depending on the manufacturer's choice. Some systems have even more than 512, but they've learned today how to make these without quite so many individual wires, and so our cables have started to get a little bit lighter again. But a channel is the electronics that are used to control each and every element of our crystal. So the receiver signals from the transducer go to the receiver, and there's 5 operations that are performed by the receiver. This sequence of operations is conveniently in alphabetical order: amplification, compensation, compression, demodulation, and rejection. The first receiver function, amplification, is also known as receive gain, and overall gain. It is not transmit gain. We've already talked about transmit gain and output gain are functions of the pulsar transmitter. Most systems today have some preamplification that occurs in the transducer before the signal gets sent to the receiver. When we're discussing overall gain, or amplification, the entire signal received from the transducer to the receiver undergoes an equal amount of amplification. In other words, the entire image is made brighter. This does not improve the signal-to-noise ratio, of course, because not only is the signal amplified, but the noise is amplified also. Amplification is adjustable by the sonographer. Its units are decibels, and typical values are between 60 and 100 decibels. So amplification, all signals received from the transducer are amplified. And so here's a small diagram that tries to show that. You get a base signal back from the transducer, and then the entire thing gets amplified, just simply making the entire signal bigger. Compensation, on the other hand, is the second receiver function, and this is what adjusts for attenuation. With compensation, signals that come from deeper tissues, which are of course weaker because of attenuation, are amplified more than signals that come from shallow tissues. This allows the image to be made uniform from top to bottom. This is adjustable by the sonographer. It's called our gain control. Usually it's called TGCs, or time gain compensation, or also depth gain compensation. In addition to the controls available to the sonographer, there are also automated compensation controls that the system applies without the sonographer having to put any input into them. The units of compensation are decibels, just like amplification. The effect on the image is that identical reflectors from different depths appear the same on the screen. This is very useful. This allows your near-field liver to look as homogeneous as your far-field liver. Synonyms for compensation are depth gain compensation and time gain compensation. With compensation, signals from deep in the tissue are amplified more than signals that are near. So here we have a drawing that shows in black the baseline amplified signal becoming compensated. The reflections in the front of it are larger than the ones at the very back, but after compensation they're all approximately the same. Compression is the next receiver function, and what compression does is it takes the signals and compresses them into a smaller dynamic range. Small echoes tend to be amplified, and large echoes are reduced. So in this picture, the green bass compensated signal is then compressed into the black signal, so some of the larger signals become smaller and some of the smaller ones become larger. Compensation is done because the dynamic range of the transducer, which is about 120 decibels, is much higher than any other part of the ultrasound system. The dynamic range of the receiver is probably around 110 decibels, and the dynamic range of the next part of the ultrasound system, what the receiver sends its information to, the scan converter, probably has a dynamic range of only about, at the most, 60 decibels. As we go through the system, the dynamic range continues to decrease until it gets to the worst component at all, which is the human eye, which only has a dynamic range of about 30 decibels. Our next receiver functions are demodulation and rectification. So I said that there seemed to be 6 parts to the receiver, and rectification is the sixth one, though we throw it in there with demodulation. Demodulation is the removal of the frequency component of the signal. So remember, when we send out a pulse of ultrasound, which is what gets our echoes to come back to us, that pulse has a frequency component to it, usually around 5 megahertz. So we don't want to see those rarefactions and compressions in our image. We want those to be removed, and that is what demodulation is removing the frequency component of the signal. After that, the signal is smoothed, and then it is rectified. Rectified means taking a signal that has both positive and negative components to it and making them all positive. So if you think of your alternating current coming out of the wall of your house, it has a positive and negative part to its signal. And then rectification takes that and just turns it into a positive, which is what gets plugged into your iPhone when you want to charge it up, or whatever other device you may have. So rectification is taking both the positive and negative portions of the signal and turning them only into positive portions. The next receiver function, continuing with demodulation and rectification, the signal is then further smoothed out by what we call enveloping, but this is just smoothing, if you want to call it that. If you need to keep it in alphabetical order, it would be smoothing. So we take our bumpy signal and then we smooth it out. Then the last piece that our receiver does is called rejection. With rejection, signals below a particular threshold that we set are rejected. The resultant signal is the A-mode signal, which is, of course, represents one scan line of your image. Let's talk about the TGC gains on our machines very quickly here, because this shows up on the SPI exam now quite a bit. There's something called the slope, and it's important. The other parts of the TGC curve are called near gain, delay, slope, the knee, and the far gain. This is almost all obsolete technology. If you really want to learn about it, I can take the old machine out of the closet and show you exactly which button adjusts the near gain, the delay, the knee, and the far gain. Not very good stuff to play around with. Made it very hard to scan, and we all rejoiced when they came out with time gain compensation such as we see today. But we still talk about the slope of our TGCs, even though we don't worry about the near gain, delay, knee, and far gain. The slope is how much amplification per centimeter depth we're going to need in order to make a nice homogeneous image. The slope in this pictures, we have a slope, a very shallow slope on the left, and what we would call a steeper slope on the right. It's shallow because it goes only from about 10 decibels or 15 decibels up to about 45. That's not a big change. So when we're looking at it, you can see here this is like 15 decibels, and this one down here is 45 on this scale of 0 to 60. That's not a huge change. You would see a slope like that in low frequency transducers because they penetrate better. We don't need to amplify as much. The picture on the right has a steeper slope. It goes from almost 0 decibels up to almost 100 decibels, so that's called a steeper slope. This is associated with, with a higher frequency probe, because it requires more amplification in the far field in order to get the same image. So you do need to understand this slope and how it's going to affect the image, and which slope is associated with low frequency transducers and which one's associated with high frequency transducers. Those will be questions on the SPI exam. Our next topic of conversation is dynamic range. Dynamic range is defined as the difference between the smallest value and largest value of any given set of values. Dynamic range can be considered the variance of a signal. It is associated with the number of available choices we have with our signal. It is always the difference between the smallest value and the largest value, and we typically end up measuring it in decibels. If we're measuring dynamic range of something with power, the decibel is 10 log of the ratio of the largest to the smallest. If we're measuring the dynamic range of any other thing besides power, then we use 20 times the log of the ratio. That's not so important. You won't need to know how to make decibels when you go to take the SPI exam. You will need to know what the dynamic range is. You'll also need to know the dynamic range of system components approximately. And by that I mean that what has the highest dynamic range? Well, just like in the body we have different tissues that have different speeds of sound, in our ultrasound instruments we have different parts of it that can handle different dynamic ranges. The transducer, as I mentioned earlier, has the most dynamic range of about 120 decibels. The receiver has the next most of about 100 to 120. Then the scan converter, 40 to 50. Then the display, 20 to 30. Our storage devices typically have 10 to 30, with most of them having the exact same dynamic range as our display today, and that's for FDA approval. And then of course the worst component that is part of our system is the human eye, which has about 20 to 25 decibels of dynamic range in grayscale. Most systems have a button on them that says dynamic range. And this is going to provide the number of grayscale levels that are available to the image. So on our left here we see a really nasty looking liver, which has a dynamic range of 72 decibels. On the right, the only difference between these two pictures is I've taken the dynamic range button and I've turned it down to 42. So these are exactly the same images. It's just the right one has been post-processed so that the dynamic range is now 42 decibels instead of 72. And you can see that there's fewer grayscale, there's fewer grays, levels of gray available to our display when we turn down our dynamic range like that. Our next topic is compression. Compression is the technique that's used to reduce the dynamic range. And so when our receiver applies compression, what it's doing is it's reducing the dynamic range. Compression introduces a few errors, but it keeps the ordinal ranking. And by that, if you have the numbers 1 through 10 in one group, those are ordinally ranked 1 through 10, of course. If we compress it so that we only are using the numbers 4, 5, and 6, they still have their ordinal ranking. 4 is the lowest, 5 is the middle, and 6 is the highest. So compression keeps the ordinal ranking. It reduces the range of values. So as an example, I like to remember the grading system. On almost any test or assignment that you can be given, you can earn something from 0 to 100 points, 100%. Well, at the end of the day, this is compressed into the grades from A to F. And with the ultrasound program, of course, this compression completely eliminates the grade D. We don't use it. If you earn a D grade, you're given an F. Seems fair. So compression is the general term for any technique that maps a large dynamic range onto a smaller dynamic range. I always like to think of Schroeder playing his piano, where he uses compression to map the grand piano of Beethoven onto a 2-octave toy piano. The net effect of compression on the signal is that the high amplitude signal is lowered, the low amplitude of the signal is raised. We have some synonyms that also mean compression. Log compression is one. Dynamic range, they mean the same thing. The units of compression are decibels, and compression reduces the range of the received signal without altering the order. This is almost always adjustable by the sonographer, and it changes the grayscale characteristics of the image. Next in our receiver is demodulation and rectification. Demodulation removes the frequency component from the received signal. Rectification converts all the negative voltages into positive voltages. With demodulation and rectification, we include smoothing, which smooths the signals out around the bumps in it. And this is something that's not adjustable by the sonographer. The last part of our receiver functions is rejection. And so rejection throws out the low-level echoes down at the bottom, which are mostly noise anyhow. This is generally adjustable by the sonographer, and it removes those low-level noise echoes and usually does not affect in any way the strong echoes from the tissues. This is showing you an A mode. Remember, we said after the receiver we're left with an A mode, and this shows you the A mode from a radial artery. We have a very strong signal right as the transducer gets past the intima into the muscularis, and then there's a very weak signal in the media, and then a stronger signal as it hits the fat on the outside of the radial artery and then fades off. Noise occurs with any ultrasound image. Noise tends to remain constant no matter what we do. In order to combat noise, we have to take our low transducer output, which creates the noise, and then increase the output, turn up the gain, and this will improve our signal strength and then hides the noise behind an improved signal. This is called an improved signal-to-noise ratio. Noise is random and persistent disturbances within our signal that we get. It tends to obscure the clarity of the echoes from the tissues and contains a lot of low-level undesirable information. Noise tends to be caused by just the heat in the body, and so it's just random signal that comes back. The signal-to-noise ratio is when we have a good comparison of meaningful information, known as signal, to the amount of contamination, known as noise. What we would call a high signal-to-noise ratio results in a nice, clean, high-quality image. What we would call a low signal-to-noise ratio results in a fuzzy image. We want a nice, clean, high-quality image. We want high signal-to-noise ratios. Let's introduce a topic called dynamic frequency tuning. Dynamic frequency tuning is the use of wide bandwidth, or many frequencies, to display selected frequencies. Frequency displayed is going to become a function of the bandwidth with dynamic frequency tuning. Remember, with ultrasound, we utilize what's known as a low Q transducer, where we have a high bandwidth compared to our center frequency. Dynamic frequency tuning automatically utilizes the signals from the high frequency portion of our bandwidth for the near field, signals from the medium mid frequency bandwidth for our midfield, and lower frequency bandwidth for the far field. And it does this automatically. Again, it is called the dynamic frequency tuning. Okay? And it's just a matter of utilizing the correct bandwidth for the correct depth. Let's discuss output power versus receiver gain. Output power, as we said, affects the entire image. It affects the entire brightness, the brightness of the entire image, and it alters the strength of the signal. More powerful pulses result in more powerful echoes, and therefore we get a better signal back. However, this is at a cost of patient exposure. Receiver gain, on the other hand, simply amplifies the return signal. This does not affect the signal-to-noise ratio, but it also does not create bioeffects in our patient. We can turn up the receiver gain as much as we want, and we will never increase our signal that goes into our patient. Patient exposure is affected by output power, not receive amplification. We always want to remember the term ALARA, which means as low as reasonably achievable. When the image is too bright or too dark, an adjustment to the output power or amplification will create the problem, correct the problem. If it's too dark, you always turn up the amplification first. If it's too bright, the best practice is to turn down the power first. When we look at output power versus receiver gain, this summary gives you a lot of good information. Changes to the brightness of the entire image, that's output power. So is overall receiver gain. Output power will alter the signal-to-noise ratio, but receiver gain will not. Output power, though, does alter patient exposure. Receiver gain does not. There is always bioeffect concerns when you're adjusting your output power. Receiver gain has no bioeffect concerns. Overall, decrease output power first if the image is too bright, and increase receiver gain if the image is too dark. Let's move on to displays. Displays, when I talk about displays, I'm talking about the monitor that we look at in order to see the image. This is an essential link between the medical staff and our system. Today we use flat panel displays, and these provide for us higher frame rates, many more lines per image than the old ones, and are generally more gooder than television screens or CRTs that we used to use. Back in the bad old days, we had what we called bistable imaging. This gave us two shades of gray. One shade of gray was called black, and the other was white. A bistable image can be represented by one binary digit. The binary digit can be 0 or 1. You can assign the 0 to either black or white, and you're left with 1 to be assigned to the other color. On our right we see a bistable image of triplets. Oh boy, wouldn't that be fun to look at? Today, of course, we use grayscale imaging, and we utilize many shades of gray. The echo strength coming back from our tissue corresponds to some particular level of gray, and the differentiation of tissue becomes possible. With bistable imaging, you can't tell that in this portion of the image here we're looking at brain matter, and here we're looking at liver and abdominal tissue. You can only tell it by looking at the surrounding outline and identifying the spine here and the greater sulcus here in order to determine what body parts you're looking at. With grayscale, of course, we can look at the kidney and say, oh, that is very different than the liver because of the echo texture that comes back from it. We have several controls in our display that help our image. The contrast control determines the range of grayscales available to us. More gray sometimes looks like a faded image compared to less gray, but there's actually more information there. Brightness determines the brilliance of the displayed image. So display controls should be adjusted on your monitor so that whatever you're scanning matches exactly what is the image in the reading room that the doctor's going to be reading your films from. Scan converters are system components that take the A mode scan and convert it into a B mode scan or B mode image. Early scan converters used two-dimensional mapping and memory cells to do this. Modern ones, of course, use a computer, and we don't have analog scan converters anymore. Analog scan converters, or anything analog actually, is what we would call real world. It has non-discrete measures, it has continuous range of values, and I always like to use the length of a string as an analog, as an example of something that's analog. A string has a length. You can measure it out to the smallest millimeter if you want, but it has a set length. We don't have to measure it. It has its own length. It's whatever it is. Digital, of course, is when it's computerized. With digital, only discrete values are allowed. So we have a couple of clocks here. On the one on the left, it's about 8:06 or so. The one on the right, of course, it is 6:38. You can tell that the one on the left, that the time is a little past 8:06 because of the position of the second hand. With the one on the right, you only know within 1 minute what time it is. So that's a discrete value. A digital scan converter will convert our images, or our A mode, into numbers. It does this through a process called digitizing. Image values are then stored in computer memory. Computer memory consists of a series of zeros and ones, what we call binary information. The computer then translates this stored data into an image for us. The advantages of digital scan converters is it gives us better image uniformity, better image stability. The image doesn't fade or drift with time, as the old analog scan converters certainly did. Digital scan converters are much more durable and are not affected by aging or heavy use. They are very fast, they have more speed, which is more gooder, and of course they are more accurate. Fewer errors occur when using a digital scan converter. Two very important elements of the digital scan converter is the pixels and the bits. Pixels are the picture element, the smallest point of a digital picture. At any given instant in time, this will be assigned a shade of gray. Pixel density is the number of pixels per inch, and the higher pixel density implies a smaller individual pixels. Spatial resolution improves with increased pixel density. Two pictures on the image here. The one on the left shows a very low pixel density, and the one on the right has a fairly high pixel density. So we're going to sum up pixels. Remember, we're talking about two things here, pixels and bits. And so we're going to sum up pixels by saying low pixel density, fewer pixels per inch, each pixel is much larger, less image detail, and lower resolution. With high pixel density, we get more pixels per inch, more image detail, better resolution. Let's talk about how bits affect our image. Binary bits are just simply binary digits. These are the smallest amount that a computer memory can handle. They have a value of either 0 or 1. Binary numbers are usually presented to us in groups of bits, and it's not uncommon for this group of bit to be 8 bits, and we call it a byte. All computer numbers are binary based, so you always have a choice of either 0 or 1. All decimal numbers that we utilize have 10 choices, 0 through 9. There are some weird terms that come with computers, and typically these consist of a byte, which is a group of 8 bits, a word, which is a group of 2 bytes or 16 bits, a double word, which is 4 bytes or 32 bits, and then something called a nibble, which is a half a byte or 4 bits. These are all just computer terms that were come up with by people thinking that this would be important to know. I personally don't think it's important to know, but it has been known to show up on the SPI exam, so somebody likes this stuff. The importance of bits, though, has to do with their shades of gray that are in each pixel. Pixel shades are determined by the value of the binary bits associated with the pixel. For each pixel, more bits equals more shades of gray. When you remember the bistable image that I showed you earlier, each pixel had 1 bit associated with it. It could either be on or off, black or white. That's not enough to give us good grayscale, though. In order to get grayscale, we have to utilize more bits per pixel in order to display grayscale. So grayscale is created by utilizing additional bits for each pixel. So if we use 2 bits for each pixel, we can have 4 different combinations using 2 bits, either the combination 00, 01, 10, or 11. And we can assign those to different shades of gray: black, white, light gray, dark gray. If we have additional bits, we can assign more shades of gray. So if we have 3 bits, we can have 8 combinations. And if we have 8 bits, we could have up to 256 combinations or shades of gray with our 8 bits. So 256 shades of gray is a very important number, because if you remember, a byte has 8 bits to it. So 256 shades of gray is what you can make out of 1 byte of binary information. The way that is done is you can calculate the number of shades of gray by just simply taking 2 to the number of bits that we're using. Remember when we had 1 bit, when we had a bistable image, that would be 2 to the 1, or 2 shades. If we have 2 to the 8, which we would have with a whole byte, we'd have 2 to the 8, which is 256. So here's a question that shows up often on the SPI exam. How many shades of gray can be displayed with 6 bits of memory? In that case, it's 2 to the 6th, which is 64 shades of gray. Well, how do you calculate this if you don't have a calculator on the exam? Well, it's very simple. You just write 2 times 2, and you write it out 6 times so that it's 2 times 2 times 2 times 2, right on out, and then you do the math. Okay, you double it, double it, double it, double it, double it again, etc. So getting back to our analogy of pixels and bits, pixels are the smallest image element, and bits are the smallest computer memory. Pixels control the image detail, and bits control the grayscale. Pixels are responsible for our spatial resolution, and bits are responsible for the contrast resolution. So why do we go through this whole process of changing our analog signal to digital for our images? Well, received signals at the transducer produce very weak echoes that are subject to noise contamination. Once we convert it into digital format, no longer can noise be introduced to our image. Many monitors also require the conversion back to analog to display the information, but most modern monitors are digital and do not even require digital to analog conversion. So let's learn how to do binary to decimal conversion. So there's a lot of ways to do this, and one example is shown on the right there. But I'm going to go through the easy way, as far as I'm concerned, the easy way to do it, and you can do it any way you want. If you're not sure how to go about this, and after listening to my method you don't like it, then simply get on Google binary to decimal conversion and decimal to binary, and find your way that works for you. Okay, so for a binary to decimal conversion, first off, you write out what I call a converter. All you do is you start out with the number 1, and you double it, and you continue doubling it each step of the way until you get a number, until you get as many numbers in the converter as you have in your binary number. In this case, we have 8 binary digits, so we need 8 numbers in our converter. Now, the simple thing is, every place where you have a 1 in your binary number, you write down the number in your converter below it. That's pretty simple. Now the complex part. Add those numbers together. So this number 10110101 is equivalent to the decimal 181. That's it. To go decimal to binary, it's slightly more difficult, but it's not really that hard. So let's take a number such as 329. We're going to create a conversion table, again, up to the number to be converted. In this case, 1, starting again with 1, doubling it again, and continue doubling it. In this case, we get to 256. If we double 256, it would be 512. Well, 512 is larger than 329, so we can stop at 256. You can put 512 in there, but it won't make any difference because it'll just be 0, as you'll see. Now, the first thing we do is we subtract from our number the largest number in our chart, which is 256. So 329 minus 256 equals 73. We put a 1 under the 256, and then we move on. Now, we can't subtract 128 from 73 without getting into negatives, so we put a 0 under the 128. We move on to the 64. Well, of course you can subtract 64 from 73, so we put a 1 under the 64. Go ahead and do the subtraction. 73 minus 64 equals 9, and we're left with 32 and 16 are of course too large, so we put zeros under them, and then we're left with 8, and we know we can subtract 8 from 9, so we put a 1 under the 8, subtract it, we end up with 1, and then we can't subtract a 4, we can't subtract a 2, so we put zeros under those, and we get down to the last one, which is 1. Of course we can subtract 1 from 1, which is 0, so we put a 1 under the 1 and we're finished. So our number 329 in decimal is 10100101 in binary. Simple, right? Let's talk about pre and post processing. There used to be a lot of things on the exam that talked about pre and post processing, and pre-processing was anything that was done to the signal before the scan converter, and post-processing was anything done to the signal after the scan converter. Today it's a lot different. Pre-processing just simply means anything that has to be done while you're still scanning. And post-processing is anything you can do if you can do it after the image is frozen. So if you can only change the setting while the image is live, it's pre-processing. If you can change it while the image is frozen, it's post-processing. Read and write zoom. We have something called a read zoom. This takes an image stored in system memory and enlarges it so that we can see the detail a little better. No additional information is acquired, the image is simply enlarged. This is a post-processing function because we're doing it with a frozen image, and I like to think of it as the analogy of a book. A book that you're reading can only be read. You can't write the book as you're reading it, it's published by a different author. Write zoom, on the other hand, allows you to be the author, and in this case a section of the image is selected for enlargement. It is re-inscenated so that more image is obtained, new information is acquired, and we get a better look at that area. The analogy is, of course, an author writing a book can add to what's already on the page if he wants to. So that's read and write zoom. Let's talk about coded excitation. Coded excitation is a transmit function that creates longer pulses. I've already talked about this as binary encoded transmission. That's exactly what it is. We call it coded excitation. This creates much longer pulses, but these pulses have binary information encoded into them. It relies on a computer to generate these pulses, and it gives us a variable spatial pulse length. There's also multiple frequencies built into the pulse. Coded excitation you can think of as a binary coding of a transmit signal. The transmit signals are encoded, and this is known as chirp or delay frequencies. Spatial compounding is a method of using sonographic information which is obtained from different inscenation angles to produce a single image. With no compounding, the signal is sent straight down from the transducer into the tissues. With compounding, on the other hand, each signal is formed to come at a slightly different angle and strike the tissue at different angles. The picture on the very left is zero compounding, or none, where the signal goes straight down. Then we see one with with 3 different angles that we're sending the signal out. And finally, at the end, we have one with 9 different angles that the signal's being sent out at. This allows us to strike curved objects or unusually shaped objects at different angles and get better specular reflection from them at least part of the time. So with conventional signals, we don't get quite as sharp as image as we do with spatial compounding. Oh, and I should mention, with spatial compounding, this can also hide information behind cysts and stones. So remember, cystic structures tend to have enhancement behind them, and gallstones, other calcifications, tend to have shadowing behind them. Well, if you're coming at it from different angles, that enhancement or shadowing can be hidden, and so it makes it harder to do diagnosis with spatial compounding. So spatial compounding can actually decrease your ability to do diagnosis while improving the beauty of your pictures. Not sure how useful that actually is. Frequency compounding is like spatial compounding, except we're going to be utilizing different parts of the frequency spectrum for different depths. Now, we already talked a little bit about this with dynamic transmit frequency. This is helps us reduce the speckle artifact, and it compounds multiple frames together at different frequencies to give us better images. This allows utilization of the entire bandwidth for the image. I said this reduces the speckle artifact. Well, I better explain exactly what the speckle artifact is, because this question has been known to show up on the SPI exam. Speckle is interference patterns from reflectors smaller than the sound wave. Edge enhancement is a process that increases contrast at the edge of boundaries. So we have 2 pictures in here, one that shows edge enhancement on the left, and in the middle, edge enhancement in the middle, and the one on the left without edge enhancement. Theoretically, I suppose the structures such as the portal vein show up better on the one in the middle. There's a picture from Wikipedia on the right that shows use of edge enhancement to enhance the spirals in this image. Temporal compounding is also known as persistence, is just simply frame averaging. Temporal compounding takes multiple frames, averages them together, and displays them as an averaged bunch of images. So by superimposing multiple frames over on each other, this improves the signal-to-noise ratio. If you want to improve the signal-to-noise ratio by twice as much, it would require 4 images averaged together to reduce the signal or the noise by half. I don't think I better say that again. That's too confusing. Anyhow, temporal compounding reduces temporal resolution. Of course, it slows down your image acquisition, and it works best with slow-moving structures. It can also assist to fill in vessels using color. Interpolation is a technique in which the areas between the scan lines are filled in with information that is just actually simply guessed at or interpolated from surrounding values. The insertion of an intermediate value of term in a series by estimating or calculating it is known as interpolation. Pixel values in our images can be interpolated and used to fill in gaps between scan lines. You can see in these images the one on the left has no image interpolation, and the one on the right certainly is using image interpolation. It makes the picture much more gooder. PACS and DICOM. These are two more systems, but they are not necessarily part of our ultrasound image. These are systems that attach to the ultrasound machine. PACS stands for Picture Archive and Communication System, and this is where we store medical information today. This has the advantages of immediate access to the images by not only the radiologist, but by anyone that wants to look at them and has access. And it also results in no degradation of data. PACS information is stored with no loss of information. Disadvantages are the initial cost. One advantage that they didn't mention here is the removal of chemicals and film processing equipment that actually is extremely expensive over the long term, though it has a lower initial cost. PACS has a very high initial cost, but it is certainly limited by the storage size. Today, most PACS systems that you would purchase at, say, a small imaging center are going to be online cloud systems that have low initial costs, and so you don't have to worry about that output of money that goes with the PACS system. DICOM, on the other hand, is the digital imaging and computers in medicine, and this is a set of protocols that allow imaging systems to talk to each other. So the way the PACS system talks to the ultrasound system is using a language called DICOM. The DICOM can also be used for CT, MRI, X-ray, or any other kind of imaging modality. Imaging information is the same for Philips, GE, Siemens, Mindray, and other manufacturers. They all speak DICOM, and they all can talk to one another and to the PACS. What ends up being stored on the PACS system is actually DICOM information. So, our different recording and archiving techniques. Paper media, we have which examples of are charts and pens, are very portable, but they're very hard to store and very bulky. Magnetic media, such as computer desks, are able to store much larger amounts of information, but they can be erased by strong magnetic fields. Photographs and film, of course, have high resolution. They're wonderful for color images, but they're bulky, difficult, hard to retrieve, and require special processing in order to create them. Optical media, such as laserdisc and compact discs, store large amounts of information. They're fairly inexpensive, and they are not subject to erasure from magnets. DICOM is the standard format for storage on laserdisc, compact disc, or other hard drive material. These require, however, a display system. Many non-standard formats for display and storage. Alright, let's get into bioeffects. Bioeffects are all about safety. The majority of the sound energy injuring the patient is going to remain there. It's going to be dissipated as heat eventually. There are several instruments that can be used to measure sound energy. One of these is the hydrophone, also known as the microprobe. This measures the pressure of the sound beam and is usually used in a water tank to determine how much pressure is getting to something. Different types of hydrophones are the needle hydrophone and the membrane hydrophone. Bioeffects can be caused by a couple of things, and one of them is the radiative force of ultrasound. This is literally the force of the sound pressing on the tissue. It's also known as a feedback microbalance. Acousto-optics are based on the interaction of sound and light. Here we see a Schiller image which allows the viewing of the shape of sound. There is some use of acousto-optics in imaging of the human body, though it's not become mainstream yet. Attenuation mostly occurs through absorption, and we said that absorption was the conversion of sound into heat. Devices that measure the output of an ultrasound's heat are calorimeters, thermocouples, and liquid crystals. Calorimeters measure the total power in the sound beam. They don't normally have a specific location, they just utilize absorption of the sound energy. Thermocouples, on the other hand, are small electronic thermometers which measure the temperature rise at a very specific location. This type K thermocouple will measure the sound only at the very tip of the probe. Liquid crystals show change in temperature by changing of color. It used to be that mood rings were very popular, and you could buy one and it would give you some kind of information concerning yourself, that it would say happy, unnervous, but all it was reading the heat coming off of your body. I don't think they're too popular these days. Let's talk about the risk-benefit relationship. Risk-benefit relationship states that the benefit to the patient must outweigh the risks of the exam. This is particularly true in obstetrics and fetal medicine. It should be noted that no confirmation of harm resulting from the use of ultrasound has been shown. Low-intensity ultrasound has no known bioeffect. We do know that high-intensity ultrasound does damage to tissue. We use low-intensity ultrasound in diagnostic imaging. There is no known cases of bioeffects with diagnostic imaging at standard intensities, with the caveat added, without the use of contrast agents. So the risk-benefit relationship, we utilize something called dosimetry. This is the science of identifying and measuring ultrasound beam characteristics. Investigators continue to study potential bioeffects of ultrasound, though to this point none have been found. A couple of important experimental terms need to be introduced. One is in vivo, which is research conducted into the living body. In vivo research, when in vitro research indicates a very high intensities can damage cells, then you need to move on and do in vivo research. In vitro research literally means in glass. In vitro research is performed outside the body and provides an opportunity to research that is impossible with live human subjects. The results of an in vitro study may not actually pertain to the in vivo situation. So we can find results of damage in vitro, but never see those same results occur in vivo. However, in vitro studies serve as a basis for design of in vivo studies, though extrapolation of the results of an in vitro study should be viewed with great caution. There's different study techniques that are used to study how the effects of ultrasound. One is called the mechanistic approach. The mechanistic approach tries to identify the specific mechanism that produces bioeffects. This is different from mechanical effects. This is a study technique to find the relationship between the cause and effect. An empirical approach, on the other hand, seeks to find a relationship between an amount of exposure and a response, without necessarily identifying what caused the response. So mechanistic, broad exposure ranges can be evaluated, but there's a lot of uncertainty about the assumptions involved. Were there other mechanisms that caused the finding? Is the effect even clinically significant? Empirical studies, there's no need to understand the mechanism. With an empirical study, if there's a finding, the biological evidence is obvious. However, different species may have different results. In general, the strongest conclusions occur when mechanistic and empirical conclusions agree. Types of mechanisms of bioeffects from ultrasound are thermal and mechanical. Thermal mechanism is simply the heating of tissue from the sound itself. Normal body temperature is about 37 degrees. When we go up as much as just 2 degrees Celsius above that, then there can be damage occurring to the tissues. With thermal effects, we have something called the thermal index. Thermal index Ti, and we also say thermal index TIS, which is thermal index in soft tissue. Thermal index soft tissue assumes sound is traveling through soft tissue. TIB assumes that at the focus there is bone. TIB, the bone thermal index, is used for obstetrical scanning. TIC is when we assume that there's bone in the near field and not at the focus. TIC is for cranial. So I like to think of it as TIS, soft tissue, S, TIB, baby, and TIC, cranial. Thermal index is a useful predictor of temperature rise. If the temperature rises 2 to 4 degrees Celsius, then this can cause, it is known to cause infertility in testicles. So we know that a 2-degree rise changes the characteristics of tissues, so we don't want to go above 2 degrees. A combination of time and temperature most likely will determine the likelihood of any kind of thermal bioeffects. If you heat the tissue for long enough, that's as bad as heating it too high for a short period of time. So both time and temperature are taken into account. With thermal bioeffects, we look at the intensity of the spatial peak temporal average, being the area that we know that the maximum heating is going to occur over time. The FDA limit for spatial temperature, spatial peak temperature temporal average intensity is 720 milliwatts per centimeter squared. It should be noted that no biological effects have been observed for temperature increases up to 2 degrees Celsius for exposures less than 50 hours. No fetal effects have been reported at temperatures less than 39 degrees C. But it should be known that bone absorbs more acoustic energy than soft tissue. Therefore, we assume that soft tissue near bone is going to have a much higher temperature than any other location. With thermal effects, we have found that empirical and mechanistic effects correlate quite well. Beyond thermal effects, we have mechanical mechanisms. These are known as non-thermal, or more specifically, mechanical, if you're taking a test. And these work by radiative force. This is the force exerted into the tissues by the sound. Radiative force results in shear stresses and fluid streaming. Cavitation is another mechanical mechanism. that occurs when there's an interaction of sound with a stabilized gas bubble. Or the creation of bubbles from dissolved gases and fluids, such as gaseous nuclei, but not from bubbles that come from contrast media. Cavitation has only been observed at diagnostic levels in lung tissue, which already has stabilized gas bodies within it. There's two types of cavitation that exist, stable and transient. Stable cavitation is just simply when the bubbles sit there and don't do anything, they don't burst. Just want to go back to that previous picture here real quick. This is what has resulted from transient cavitation hitting this brass impeller. It's caused, you can see the damage caused by cavitation alone. Anyhow, stable cavitation is when gaseous bubbles will expand and contract, but they don't burst. In this case, much of the energy of the sound is absorbed by the bubbles. Stable cavitation is associated with microstreaming and shear stresses. And if we go back 2 slides, remember the radiative force part here, shear stresses and fluid streaming. That's going to be associated with stable cavitation. So again, stable cavitation, microstreaming, shear stresses. So we have stable cavitation is just the expansion and contraction of the bubble with time due to the compression and rarefaction of the sound. Inertial cavitation or transient cavitation or normal cavitation, they're all the same thing, what happens is the bubble gets contracts and gets bigger, it contracts and gets much bigger, and then eventually it contracts and implodes. This is cavitation or transient cavitation. Transient cavitation at high mechanical index levels results in bubble bursting. This is also known as inertial cavitation and normal cavitation. It's not considered clinically significant. However, it can occur when the pressure is only 10% more than stable cavitation. Transient cavitation produces very highly localized effects. It has very violent effects. It results in colossal temperature changes, such as up to 4,000 degrees Kelvin. However, it's very, very localized. It's in a very small place. And it does cause shock waves or enormous pressures to occur. Our summary of cavitation is that stable cavitation is simply oscillating bubbles associated with microstreaming and shear stresses and occurs at a lower MI, mechanical index. Transient cavitation, also known as transient, inertial, or normal, TIN, is associated with bursting bubbles, shock waves, very high temperatures in a very localized area, and higher mechanical indexes. Well, what is this mechanical index I keep mentioning? We already talked about the thermal index. The mechanical index is really the best indicator of mechanical bioeffects from cavitation. There's 2 sound wave characteristics that are utilized to compute the mechanical index: peak rarefaction pressure and frequency. There's a higher risk of cavitation when we have higher rarefaction pressure and lower frequency. The equation for mechanical index is shown here, peak rarefaction pressure divided by the square root of the frequency. This is a good equation to memorize. However, you will not be expected to do any calculations with it on the registry exam. That concludes our mechanical index. Let's talk about epidemiology. Epidemiology, or population studies, they can be empirical. They utilize often clinical surveys. When the occurrence rate of a bioeffect is small, it's going to require many subjects in order to find the bioeffect causing the problem. The smaller the effect, the harder it is to detect. So why do they do epidemiologic studies? Well, it's because even though at this point we don't know of any harm that can come to people from ultrasound, a very high percentage of women in the United States are scanned with ultrasound during their pregnancies. We assume that there's a small risk concerning exams performed and without leading to disease. If a harmful effect is present, though, it may affect a fetus for life, and so we want to be very careful in making sure that we know as much about ultrasound as we can. Currently, no adverse fetal outcomes are associated with ultrasound exposure. Epidemiology, there's some limits to it. The limitations of epidemiological studies is that studies are often retrospective, which means we think we see a problem and we go back and look at the old records and see if we can find the cause of the problem. Unfortunately, there may be ambiguities in the data, because who knows what the justification for the ultrasound exam was? What exactly was the gestational age when the scan was done? How many exams did the patient have? What was the exposure time of each exam? What was the technique used to do the exam? These are all ambiguities that could lead to different results. Bad outcomes may occur, but may not be due to the ultrasound. So if we see a problem with babies being born, it could be also environmental factors, poor nutrition, smoking, alcohol abuse, drug abuse, or perhaps it's the sound of jackhammers. Let's talk about prospective and randomized studies. The best epidemiological studies are prospective and randomized. A prospective study means that we're going to set up the study before we collect the information. It's randomized. One group is exposed to ultrasound and the other abstains. Other risk factors can then be excused. Turns out parachutes are something that no one has ever done a prospective and randomized study on. Their effectiveness has not been proven. Of course, nobody has volunteered to be the person to jump out of an airplane without one. The AIUM official statement on epidemiology for obstetric ultrasound concludes that the epidemiological evidence based on exposure is based on conditions prior to 1992, and no studies have there is insufficient justification to warrant conclusion of causal relationship between diagnostic ultrasound and adverse effects in humans. So basically, we haven't seen any problems yet. And then they make the caveat that this was done prior to 1992, when the limits of ultrasound were raised substantially. In fact, they were raised 10 times. Clinical safety and prudent use of ultrasound. Conclusions of the AIUM state that no confirmed harmful bioeffects from exposure to diagnostic ultrasound have been reported. It's possible that bioeffects may be identified in the future. However, the benefits to the patient currently outweigh the risks. It's totally appropriate to use diagnostic ultrasound prudently to provide a benefit to the patient. It's inappropriate to use diagnostic ultrasound in a non-medical setting for entertainment. However, when we look at a quick Google search, we see many sites set up to do ultrasound just for entertainment. The AIUM statement on safety in training and research basically says that though there are no confirmed adverse biological effects on patients from this usage, we can still go ahead and use ultrasound for training and research purposes, even if it does not provide a benefit to the patient. Probably more important than the ultrasound is the electrical safety of our equipment. Precautions such as proper electrical grounding should always be used. Instruments should be checked regularly, and transducers in direct contact with patients possess the greatest risk to the patient's safety. And in fact, shock from a cracked transducer housing is the greatest risk that a patient faces. Less significantly, the image may be compromised when using damaged transducers. Overall safety considerations are that only perform studies with a valid medical justification. Don't prolong the study without medical justification. Minimize the exposure time. Minimize the power and maximum amplification to optimize the image. Always practice Solera. Be prudent, careful, and judicious. Be a professional. Alright, let's move on to the next subject, which is harmonics and contrast agents. So, fundamental imaging consists of imaging at the frequency that we have selected for our probe. Harmonic imaging is imaging at twice that frequency. So what we find is that sound will travel slightly faster in compression than rarefaction. This is a nonlinear behavior that results in the formation of harmonic distortions to the frequency signal that we send out with our pulse. The strongest harmonic distortion occurs at twice the fundamental frequency, and this is called the second harmonic frequency. So a 5 megahertz frequency will develop a second harmonic at 10 megahertz. Harmonic imaging can improve your images, however, in some cases it may not. So my rule of thumb is always, does harmonics work? Well, turn it on. If it got the image better, then yes, it worked. If it made it worse, then turn it off because it didn't work so well. So again, as I said, wave distortion occurs because the sound moves slightly faster in compression than in rarefaction. This causes harmonics and eventually sound wave distortion. Fundamental imaging is created by processing the image, the frequency of the signal that came back at the frequency that was transmitted. Harmonic imaging uses only reflections that were created utilizing the harmonics in the signal reconstruction. The information from the fundamental frequency still exists, but is suppressed. Turning on harmonics does not create harmonics. Harmonics already existed before you push the harmonic button. However, what it does is it allows the ultrasound machine to filter out the fundamental frequency and then create the image by only listening to the harmonic frequency bandwidth. Linear and nonlinear behavior. With linear behavior, we mean proportional. Linear systems respond proportionally to a signal. Nonlinear systems will respond disproportionately to a signal in what we call an asymmetric manner. In the development of harmonics, harmonics are created because nonlinear effects are occurring. When we think of harmonics in the near field, we don't utilize it generally for imaging because the only frequency available is the fundamental frequency. The harmonics have not developed yet. In the midfield, we can utilize harmonic imaging because the harmonics developed and the returned echo is still strong. There's been no distortion by superficial layers, and so we get good spatial resolution with our harmonic imaging. In the far field, we don't utilize harmonics generally because the harmonic signal, which is twice the frequency of the fundamental signal, are absorbed by the tissues much more rapidly and attenuated, and so we don't get the signal back to the transducer. So as a general rule of thumb, we can say, where are harmonics useful? In the midfield. Why? Because they haven't developed in the near field and they're absorbed in the far field. One thing you should know about harmonics is they only develop when there is a strong enough beam strength to create them. Therefore, the weak portions of the beam will not create harmonics. When we look at the beam shape, only the mid portion of the beam is strong enough to create harmonics. Therefore, the lateral resolution is improved with harmonics because the beam is much narrower. So our summary of tissue harmonics is that they're not present when the pulse leaves the transducer. They're created in tissues during transmission. They're created by nonlinear behavior, specifically that sound moves in compression faster than in rarefaction. And they're created only along the main beam of the axis. So, there's a technique of improving harmonic imaging known as pulse inversion. This reduces the reflections from the fundamental frequency. There's two means to reduce the fundamental frequency. One is by the use of filters and the other is by pulse inversion. Pulse inversion helps cancel out echoes from the fundamental frequency. A pulse is sent out and then at the fundamental frequency, and then a second pulse is inverted and sent along the same scan line. Echoes from the second pulse are added to the first pulse, and if you remember, when pulses are inverted, they will cancel each other out. The only signal that remains is that from the harmonic frequencies. So pulse inversion is a technique that manufacturers developed to get better harmonic images. Fundamental frequencies follow linear behavior and will destructively interfere with one another. Harmonics are nonlinear, and so after the destruction of the fundamental frequency, the only thing left is the harmonic. There's a disadvantage to the pulse inversion technique in that it increases the time to obtain the signal, as you must send out two different signals. So harmonic imaging in general, you get decreased reverberation, decreased beam aberration, decreased beam side lobes, decreased beam width, which improves lateral resolution, decreased haze, decreased temporal resolution, improved axiolateral and contrast resolution, and improved cystic clearing generally. It also gives better imaging of Rayleigh scatterers. Sometimes the Rayleigh scatterers become so strong that it makes the cystic structures appear cloudy. Another manufacturer technique to improve harmonics is known as power modulation. In power modulation, two successive pulses are sent out. The second pulse has twice the strength of the first pulse. Remember, the harmonics are not developed unless a pulse has a certain level of strength to it. So the first pulse does not create harmonics. During reception, reflections from the first pulse are then amplified to match the second pulse and then subtracted from the second pulse. The resultant reflections are only the harmonics that are nonlinear and are left over. Now with harmonics, it's important to discuss contrast agents. Contrast agents consist of microbubbles in ultrasound. And in contrast agents, gas bubbles that are encapsulated in usually a fatty shell are injected into the body and then imaged with ultrasound. There's 5 requirements for contrast agents, and they are that they must be safe, metabolically inert, long-lasting, strong reflectors, and small enough to pass through the capillaries in the lungs. Contrast agents, because of the way they reflect sound, create much stronger harmonics than tissue. Contrast harmonics, as opposed to transmission harmonics, are created during reflection of the sound. Contrast bubbles exhibit nonlinear behavior and expand. Bubbles will expand during rarefaction much more than they will during compression. This creates a resonant peak between 2 to 4 megahertz. Peak rarefaction is much more important than compression with regard to contrast harmonics. Here we see contrast harmonics in this liver compared to the liver without the contrast. The amount of contrast harmonics is estimated by the mechanical index. As the mechanical index increases with lower power and stronger wave output, there's a nonlinear action of contrast bubbles. At low MI, less than 0.1 MI, no harmonics are formed in the contrast agents. At what we would call mid-MI, or 0.1 to 1 mechanical index, we start seeing small harmonics. At greater than 1 mechanical index, we get extreme nonlinear behavior, and large harmonic signals are created and bubble disruption occurs. Bubble disruption will create great amounts of harmonic reflection. An important characteristic that determine the contrast agent's stability and longevity in the bloodstream of the contrast agents is the nature of the outer shell and whatever the gas is that fills the microbubble. Shells that trap the gas and increase bubble life. Shells trap the gas and increase the bubble life. This can be done with agitated saline, which rapidly dissolves in blood. There's a flexibility needed for expansion and contraction, and sometimes rigid shells will disrupt too easily. Let's talk about artifacts, much more interesting than contrast material. What is an artifact? Artifacts are reflectors that are not real, that are seen on the image. They can be incorrect shape or size, incorrect position, or incorrect brightness. What causes artifacts? Well, artifacts can be caused by a violation of the assumptions. All machines are manufactured with certain assumptions in them, and we'll talk about those assumptions in the next slide. What else can cause artifacts? Equipment malfunction. Sometimes the equipment that you use malfunctions. Also, just simple physics can cause artifacts. And lastly, operator error can cause artifacts. So the 6 assumptions that manufacturers assume when making an ultrasound machine is that sound travels in a straight line. Sound travels directly to a reflector and back, and sound travels exactly 1540 meters per second in soft tissue. Reflections arise only from structured position along the beam's main axis. The imaging plane is very thin, and the strength of a signal is related to the characteristics of the tissue creating the reflection. And we know already that some of these assumptions are patently false. Sound does not ever travel at exactly 1540 meters per second. It only does so in the mythical soft tissue that is an average of the soft tissues in the body. Sound travels different in every tissue that it encounters. So the assumptions are that all ultrasound machines have to be designed to follow these 6 basic assumptions, but artifacts will appear when the assumptions are not true. Most artifacts can be explained by determining which assumption was violated. Actual anatomy will remain visible when the window or orientation is changed. So if you're seeing an artifact, change your window, change your orientation, and real anatomy will stay there. Artifacts will go away, or could go away. Instrument malfunctions appear as obvious artifacts and they never resolve. When you see an instrument malfunction, call your service engineer. So let's talk about some of the artifacts that occur in ultrasound imaging. Reverberation is one of the most common artifacts that we run into. It's a type of multipath artifact, and it appears as multiple evenly spaced echoes caused by sound waves bouncing between 2 strong reflectors. Its characteristics is that it appears in multiples, they appear evenly spaced, they're located parallel to the main axis, and at ever increasing depths. This violates the assumption that sound travels directly to a reflector and back. And in fact, what it does is it travels directly to a reflector, back, and back again, 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 and that causes the reverberation artifact. Comet tail artifacts are a type of reverberation artifact, but they're known as comet tail or ring down artifacts. This is a solid reverberating line. It is generally hyperechoic, and it consists of multiple lines without the space in between. Comet tail artifacts arise from gas bubbles, resonating structures, metal structures, and vibrating structures. So a BB, if it gets lodged under the skin, would cause a comet tail artifact. Many comet tail artifacts are seen with surgical staples. And again, this violates the assumption that sound travels directly to a reflector and back. You may ask yourself, why does this reverberation cause a comet tail artifact? Well, if you think about a structure suspended in the body, such as suspended like this bubble within these other bubbles, vibrating when the sound hits it. So a little BB or small staple will vibrate when the sound hits it, and that vibration causes the ring down artifact. Here we see ring down artifact at the interface between the lung and the liver caused by pleurisy. Also, if you're looking for patients with COVID, you'll see this on them. Shadowing is another artifact that is caused, and this is a hypoechoic region posterior to high attenuation. Shadows appear in the same background color. Shadows appear as the same as the background color of your image. So in this image of this black on white photo, or ultrasound, you see a shadow, a critical angle shadow at this change of structure here, and it appears white. In this structure, which is white on black, the shadowing appears darker, or black behind the stones that occurred. Shadowing is the result of too much attenuation. and it prevents visualization of the true anatomy. In fact, no sound is getting behind these gallstones, and so therefore we can't see what's back there. Shadows may provide important diagnostic information needed to characterize the tissue, such as, is that a stone? Well, does it shadow? Yes. Okay, therefore it is a stone. So this violates assumption number 6, which is the strength of reflections is related to the characteristics of the tissue creating the reflection. Now I want to take a second just to mention to you that at no point ever will they ask you what number assumption is being violated by this artifact. We just listed the artifacts as a guide to help you understand what's causing them. You don't have to memorize the 6 different assumptions. Edge shadowing, such as we saw in the previous image, is shadowing that occurs at the edge of a curved reflector. It's also known as a refraction shadow or a critical angle shadow. Generally, this results in a hypoechoic region past the curved edge. This violates the assumption that sound travels directly to a reflector and back. In fact, in this case, sound will travel directly to the reflector and then be absorbed along the reflector, creating the shadowing area. Enhancement artifacts are simply hyperechoic regions behind tissues. This is due to too little attenuation. This is located deep to tissue with low attenuation. Enhancement also provides important diagnostic information required to characterize the tissue. This again violates assumption number 6, which is the strength of the reflection is related to the characteristics of the tissue creating the reflection. Also, if we think about our spatial compounding can come in at different angles and wipe out the enhancement, thus removing this ability to diagnose things such as cysts with standard ultrasound. Be sure if you're looking at what you think is a cystic structure, if you don't see enhancement behind it, that you turn off your spatial compounding, and then you may see the enhancement. Focal banding is a type of artifact that can occur. It can be a shadowing band or it can be an enhancing band. Typically this is most prominent at the focus because the signal that comes to the focus is much stronger than the other signals of the other reflected signals. But it also can be due to an equipment malfunction. A dark band is often associated with annular array transducers and is the type of banding that is caused when their crystals fail. Also important to note is that nobody uses annular array transducers anymore. A mirror image artifact is when sound travels off of a strong reflector, strikes another reflector, and then returns to the transducer. The redirection causes a second copy of the structure to appear. We always can recognize mirror image artifacts because the mirrored structure is always located along a straight line between the transducer and the artifact. The mirrored, let me reread that. Mirrored structure is, so in this case it's a straight line to the mirrored structure here. So sound travels in a straight line, hits the reflector, bounces off the structure, and goes back to the transducer. This can also occur with Doppler. It's not uncommon to see a second vessel deeper than the real vessel, especially when looking at the subclavian artery or vein. Characteristic of mirrored artifacts is that the second is a copy of the true reflector. The artifact is always deeper than the real structure, and a strong reflector, the mirror, is always between the artifact and the transducer. The true structure and the artifact are equal distance from the mirror. So if we go back and look at that we see our strong reflector directly between the real structure and the mirrored structure, and both structures are equal distance but from the mirrored structure. And that holds up true when looking at this set of characteristics. A unique artifact that occurs only with spectral is called spectral crosstalk. Now, Dr. Edelman in his book calls spectral crosstalk a mirror artifact. It is in fact not a mirror artifact because there's no central reflector causing the display to be reflected below the baseline. This is actually caused by an overgain signal of the Doppler signal or scanning far too close to 90 degrees. When you get close to 90 degrees, you get something called inherent spectral broadening, and this can occur and give you the crosstalk artifact. Let's talk again about lobe artifacts. We discussed lobe artifacts earlier, but let's bring them up again. So side lobe and grating lobes are due to energy being transmitted in a direction other than the beam's main axis. And this violates the assumption that reflections arise only from structures positioned along the beam's main axis. Remember, side lobes refer to these occurrences in a single crystal transducer. Grating lobes are what we see today in the multi-element phased array transducers. Side lobes arise only from single crystal transducers, and grating lobes are created by phased array transducers. These create a lateral displacement artifact. To reduce lobe artifacts in phased array transducers, we use two techniques: subdicing and apodization. Refraction is an artifact in which sound changes direction along a path. This creates a lateral displacement artifact, and a copy of the actual reflector is made off to the side, usually at the same depth as the actual reflector. This violates the assumption that sound travels in a straight line. Artifacts from spatial resolution or detail resolution occur when two or more reflectors display as only one on the image because they're too close to be resolved. Of course, we know that this is from axial, lateral, and elevational resolution limitations. Elevational resolution, or slice thickness, results in a partial volume artifact. Elevational resolution, or the thickness of the beam perpendicular to the imaging plane, displays reflectors in front of or behind the displayed image. This results, of course, in the slice thickness artifact, in which, as we know, the thinner slices provide the best target resolution, and thicker slices allow averaging of material together. So if we have a target that's wider than the image slice, it'll be completely resolved correctly, as you see in this radial artery. However, if the target is smaller than the slice thickness, then we will not be able to resolve it, and we'll see information averaged together with surrounding material, creating an artifact. Here's an example of that. We see that the focal zone is best with tube A, and we can distinguish tube A quite clearly. However, the thickness of the beam, even though there's a focus near it, is too thick in order to clearly see tube B. Here is our radial artery again. When we have the correct focal position, we can see the artery, and when it's incorrect, we can't really see the artery, mostly because the slice thickness error, even though in our lateral resolution we have multiple foci up. Axial resolution is when two objects along the path of the beam are too close to resolve. Lateral resolution occurs when objects that are wider or closer together than the beam width cannot be resolved. Multipath artifacts are any artifact that occurs when sound reflects off of another structure instead of returning directly to the transducer. Reverberation is a type of multipath article, and so are mirror image artifacts. Anisotropy causes its own type of artifact. Anisotropy literally means not isotropic. Isotropic means the same from all sides. So anisotropy means it's different from different angles. Specular reflectors, such as tendons and nerves, are very anisotropic reflectors. If you're close to 90 degrees, the probe will return strong signals than if you are at oblique angles. This is an image of a supraspinatus tendon in the shoulder, and when we are at a slight angle so that the tendon fibers are reflecting slightly downward, the sound comes down and reflects off and doesn't get back to the transducer. If we rotate the tendon slightly or heel toe the transducer so that the fibers are now nearly horizontal to our beam, then the reflection comes back to our transducer, and we're able to see that there are fibers in this area and everything is normal. Please note that as we look at the tendons in this area, they look pretty good, but when we rotate our image, you see it drops out over here due to the anisotropic effect. Speed error artifacts is when sound propagates through tissue or medium at a speed other than 1540 meters per second. In this case, the depth becomes incorrect. This is also called a range error artifact. It violates the assumption that sound travels 1540 meters per second in soft tissue. It's important to know that if the speed of the media is faster than 1540 meters per second, objects will be displayed as shortened on the image. If it is slower than 1540, they will be displayed as elongated from near to far field on the image. Range ambiguity artifacts are speed errors. In this case, we see the cyst in the liver has caused a change in speed because it is a watery substance. And we'll see the diaphragm come down, drop a little bit because of the speed in that cyst, and then drop again when we get to the other side of it. So the echoes in that lesion cause some delay, creating a speed error artifact. So if the medium is slower than soft tissue, sound travels slower than expected and the round trip time is too long, and the machine will assume that the structures are deeper than they really are. If the medium is faster, then the sound travels faster than expected and the round trip time is too short. So let's take a look at some actual images. Here we see an evaluation of a implant that is in vitro, so it's in glass, so it's sitting in a container with water, and you can see that the implant is saline and the sound gets to both the bottom of the implant at the same time it does through the saline. When we use a silicon gel, which sound travels slower in, then it elongates the base of the image and appears to be much deeper. The beat of sound in this is about 970 meters per second through this image. In vivo, we can utilize this to determine what type of implant the patient had. So a saline implant, the pectoralis major will be contiguous behind the implant. In a silicon implant, the pectoralis major, there is a drop-off due to the speed error artifact, and you can see the wall simply drop off and then go behind the implant. Range ambiguity artifacts can also cause objects that are strong reflectors but are outside of the range limit of the ultrasound machine to be assigned a location in the wrong position. This is because the pulse from the previous pulse is still traveling back to the transducer when the machine thinks that this area needs to be has been insulated. These type of range ambiguity artifacts, where an object outside of the range, the depth of our image, have largely been eliminated due to binary encoded transmission, also known as chirped or Gallet coding. This is an example of a speed error artifact where you see what appears to be an IUD anterior to the endometrium. And it turns out that in fact there is a problem with the GE Logic 9 that causes this a strong reflector to appear when it has a significant speed difference too close to the transducer than it really is. Electrical interference can occur when you see this noise on the machine. There's nothing you can really do about it. It's caused by interference from nearby electrical equipment. It's often seen in the operating room due to the use of bovies to coagulate bleeding during surgery. We talked a little bit about acoustic speckle earlier. Again, speckle is noise resulting from constructive and destructive interference reflections returned from structures that are smaller than the wavelength of the sound. These appear as grainy tissue-like texture on our ultrasound. Speckle can be reduced with compound imaging and special speckle reduction technology that is machine specific. Here we see an image with speckle on the left and reduced speckle in the image on the right. Harmonic imaging, of course, can reduce the noise in the image. It increases the signal-to-noise ratio, and it also can narrow the beam width. It improves lateral resolution and can make the image much better. Also, it can degrade the image, so you may need to turn it off. Our next subject is going to be quality assurance. So quality assurance is what is done in the lab to validate the consistency of ultrasound images and the accuracy of the measurements. It must be done, so here's a test answer. Quality assurance must be done routinely and periodically. It is the responsibility of the sonographer. Period. That answered 2 test questions. Quality assurance requirements are the assessment of the system components, making sure that repairs are done properly, doing preventative maintenance, and record keeping. The goals of quality assurance is to guarantee proper operation of the system. It helps to detect the gradual changes that occur over time. and is done to minimize the downtime of our equipment and to make sure that we're able to scan more patients, not like we're doing enough already. It helps to reduce the number of non-diagnostic exams that are performed and reduces the number of repeat exams. Some of the devices used in quality assurance include the tissue equivalent phantom, the Doppler phantom, and the beam profile slice thickness phantom. The AIUM 100 millimeter test object was used for many years, but is now primarily only used by engineers and technicians that are designing and building the equipment or maintaining the equipment. Methods of quality assurance are to test under known defined conditions, do it consistently, use constant instrument settings, use a phantom with measurable characteristics, and to image in an identical environment each time. The objective versus subjective standards of quality assurance are that objective standards are unbiased, factual, repeatable, and countable. Objective information is the same even when obtained by different people. Subjective statements are influenced by a person's individual experience. However, they are based on reality, and they are colored by a person's perspective. They can't be verified using facts and figures. I'll give you an example of a subjective statement. If your instructor walks up behind you and says your image is too bright, please turn it down, use your gain, then that is certainly a subjective statement. However, it's based on their perspective and based on reality and their experience. However, an objective statement is, if your instructor walks up behind you and says, you need to adjust your TGCs because you don't have enough gain in the near field, that's objective because everyone can look at it and see that the liver in the near field is too dark compared to the far field. So these are the difference between objective and subjective statements. Quality assurance should be based on objective standards, should be based on measurements free of personal or biased perceptions. The tissue equivalent phantom all have ultrasonic features similar to soft tissue. This is utilized to evaluate grayscale, tissue texture. You can utilize it to identify where the focus is at and to be consistent. Tissue equivalent phantoms have a speed of sound at 1540 meters per second. They attenuate consistently. They have similar scattering characteristics and similar echogenicity. The grayscale is able to be evaluated as the phantom contains many small scatterers, usually made of graphite, that mimic soft tissue. Structures include anechoic, hypoechoic, and hyperechoic areas for evaluation of spatial and contrast resolution. The point reflectors that are seen in tissue equivalent phantoms are typically nylon strings that are located throughout the phantom. Doppler phantoms are designed to measure circulation structures. There are three types of Doppler phantoms: the fluid flow phantoms, string phantoms, and moving belt phantoms. All of them have different drawbacks and advantages. No phantoms for Doppler have been approved by the AIUM for quality assurance at this time. Slice thickness phantoms are specialized phantoms to determine elevational resolution. However, as we learned in the lab, you don't have to buy an expensive slice thickness phantom in order to make this measurement. Performance measures are things that we measure consistently, or as we would say, routinely and periodically, in order to determine if our imaging machines, our ultrasound machines, are changing with time. Some of the performance measures that we make are sensitivity. This is the ability of the system to display low-level echoes. It's normal when all pins, solid masses, cystic structures are accurately displayed. When the output power in TGC and amplification are adjusted to a normal sensitivity, we would see normal sensitivity. All subsequent quality assurance measurements would be made at this normal sensitivity, and the settings should not vary from one routine evaluation to the next. Maximum sensitivity is when output power and amplification is set to the maximum practical levels. Depth of the tissue is measured. Depth of the tissue-like structure is measured to determine maximum sensitivity. This should not vary from one routine evaluation to the next. An alternate measure is to turn the system brightness down until we get to full brightness or saturation, from minimal brightness to saturation. The dead zone is a region close to the transducer where images are inaccurate. This results from the transducer ringing during the time it takes for the machine to switch from transmit to receive mode. This can be assessed with shallow pins near the surface of the phantom. Higher frequency transducers have less dead zone than lower frequency transducers, and in fact most new transducers have minimal, if any, dead zone whatsoever. Standoff pads allow for accurate imaging of superficial structures if they are within the dead zone. An increasing dead zone depth may indicate a cracked crystal, detached backing material, or longer pulse duration, all things to be evaluated. Registration accuracy is the ability of the system to determine if its measurements are accurate. Range accuracy is in the vertical depth calibration, when you measure set pins and determine if they are producing the correct calibration. Accuracy in reflector depth can occur in A mode, M mode, or B mode imaging. Horizontal accuracy is the ability to determine the accuracy of echoes in the perpendicular to the sound beam. In this case, again, calipers are used to check the direction, and you determine if the accuracy is still correct. Axial resolution is detail resolution in which the smallest distance at which two pins positioned parallel to the sound beam are displayed as two distinct echoes, as we see in these images. These reflectors cannot be separated completely. These can. And these, of course, in the vertical certainly can. Lateral resolution. Oops, I don't think I had my... Okay, here we go. These cannot be separated. These can, and of course these in the vertical can. Lateral resolution is the minimum distance side by side in which pins can be displayed two distinct images. So here we see these are blurred together, but these, there's a gap that we can see, and perhaps maybe this gap is the one that is best for the lateral resolution. Remember that lateral resolution is determined only on beam width. Compensation uniformity, or as most people would call it, contrast resolution, is the system's ability to display similar reflectors with echoes of equal brightness. When we look at these different reflectors, these have equal brightness within each of them, but not between them. With proper TGC settings, the reflectors should have their own brightness displayed. In this case, the brightness of the surrounding tissue and these holes here should be equal top to bottom. Mock cysts and solid masses. Phantoms generally are filled with things that appear solid masses and with cysts, and you should be able to see them with your system. Display hard copy output and grayscale dynamic range. Adjusting the system's output power and amplification should produce predictable changes. Ultrasound system displays should be viewed on multiple display devices such as remote viewing systems. Let me rephrase that. What you see on your screen should be exactly the same as what they see on the screen in the reading room. We can test this by utilizing something known as a SMPTE test pattern. So the Society of Motion Picture Test Engineers came up with this test pattern. We can put this on our machine and look at it, and then go into the reading room, and if it does not look identical on both machines, then we need to adjust our display devices. One measure of quality assurance between different labs is the specificity and sensitivity of the exams. What the specificity and sensitivity tells us of our exams is whether or not we are finding disease. So we have to ask ourselves, what is a test? We're going to utilize the chi-square test in order to determine our sensitivity and specificity. So a test is something that we do to determine if a patient has a disease. There's only two results. The patients have disease, the patients do not have disease. Whatever the best test is, it's called the gold standard. A chi-square test compares any other test to the gold standard and gives you a sensitivity and specificity, positive predictive value and negative predictive value, and an overall accuracy. So the gold standard, as we said, shows either there was disease, the test is positive, or there was no disease, the test is negative. If we use another test and compare it to the gold standard, this other test will either show that there was disease and it's positive, or there was no disease and our test was negative. If both the gold standard and the other tests match, we call that a true positive. If the gold standard and the other test match and it's negative, we call that a true negative. If our test calls it positive, but the gold standard says that it's negative, we call that a false positive. And the worst case scenario is when our test says that it was negative, that the patient had no disease, but they actually had disease and it showed up in the gold standard. That's known as a false negative. So sensitivity is our ability to detect disease. It's also our ability to detect a small prevalence of disease. Sensitivity is measured when we take the true positive divided by the true positive plus the false negative. Now I'm going to go back real quick and I'm going to show you something on our chi-square test. let's put sensitivity in blue, and we're going to say this column here is our sensitivity column. Okay? We're going to say specificity is this column here. This is our specificity column. Now, it would make sense, since we're also going to be measuring positive, to have positive in this column here. So our what we call our positive predictive value is taken from this row, and our negative predictive value is taken from the other row. Since this is pretty easy to remember, since this says positive and this says negative. Now, one other type of measurement we're going to be making is known as the accuracy. And the accuracy, and this is important, takes everything. Okay? Now let's go see how this works with the our sensitivity and specificity. So there's one equation you're going to have to remember, and that is true over everything. So with sensitivity, it is the true positive over everything in the sensitivity column. With specificity, it's the true negative over everything in the true negative column. Let's see, how do I turn this off? Okay, so this is the true negative over everything in the specificity column. With our positive predictive value, remember that's this row, it is the true over everything. It's the true positive over everything. True positive plus false positive. Negative predictive value is the true negative over everything. False negative plus true negative. And accuracy is true over everything, which is just simply the true positive plus the true negative over all of the measures combined. Okay, so let's go look at the actual equations. Hold on. Alright, so sensitivity is our ability to detect disease. It's our ability to detect disease, a small prevalence of disease. Let's look at all of these equations. Sensitivity, true over everything in the sensitivity column. Specificity, true negative over everything in the specificity column. Positive predictive value is true over everything in the positive row, and negative predictive value is true over everything in the negative row. Accuracy is again everything true over everything. So these are the equations, but all you have to remember is true over everything. So specificity is our ability to determine a disease is not present. That's our specificity. Our false positive is if our test is incorrect because it does not match the gold standard, this is the percentage of times that the test is positive for the disease it turns out to be true. False negative, the test is incorrect because it does not match the gold standard and the test was negative for the disease. False negative, moving on. Okay, true positive and false negative. We already talked about those. Accuracy is always, this is important, accuracy is always between the sensitivity value and the specificity value. Accuracy is also between the positive predictive value and the negative predictive value. So if you're given a long drawn out question but you're given the sensitivity and specificity, and you're asked which of the following could possibly be the accuracy, as a multiple choice question typically can give you. Look for the answer that has the accuracy between sensitivity and specificity and between positive predictive value and negative predictive value. Often they will give you these values. You don't have to calculate them, and so you know the accuracy must be somewhere between them. At worst, you can narrow it down to one or two possibilities. That wraps up sensitivity and specificity, though that is only a review of it. Elastography is one of the newer technologies that is going to occur in ultrasound, and we need to talk about it real quick. Elastography is the ability to look at structures and how they deform under stress. So here the spoon is putting stress on the jello. Everything deforms except for the almond in the bottom. Elastography would be essentially just taking a picture of that right there. How does elastography work? A mechanical force is applied to the tissue and the amount of strain is measured. Remember, force is applied and strain is the deformation. So elastography was initially done by taking the transducer and pushing down with it to deform the tissues. Today we do elastography with a mechanical force that is much easier to use. That is simply the longitudinal mechanical wave that forms sound. So we can still push with the transducer, but in many cases we don't have to. We just utilize the sound itself to do it, which causes a pushing or vibrating of the surface with a probe. So the radiative force of ultrasound can be utilized to push inside the tissues in techniques called ARFI and SWI and SSI. And there's another type of force that can be applied called transient elastography, which is used in a proprietary method called the FibroScan. So strain imaging is actually utilizing the ultrasound probe and pushing on the tissue to cause deformation, and then imaging that deformation typically with color in order to see how much deformation has occurred. This is a very cheap and colorful way of doing it, but it's very difficult to reproduce. And since it's qualitative only, we get no quantitative stiffness data. Objects move in and out of the plane during compression. There's some difficulty utilizing this with deep structures. With shear wave elastography, a pulse of sound is sent into the body, and a shear wave is created which transmits to the side of that sound pushing downward. This shear wave is utilized to measure the deformation of the tissues, because it will change speed based on the stiffness of the tissues it's going through. So similar to the ARFI, this is the acoustic radiative force imaging, ARFI. There is another type that is known, you can use acoustic radiative force, and this is done with MRI or ultrasound, and it provides one pulse will provide the entire elastic map. Then there's something called supersonic shear imaging, which uses the shear wave elastography imaging to produce multiple near simultaneous pulses that travel at supersonic speed, and this can then detect shear waves at more than 10,000 frames per second in deep organs. So this is turning out to be the very best method of elastography. Hybrid imaging is a new imaging technique where they take CT or MRI information and overlay it on top of the ultrasound information, giving us both ultrasound and CT together. It's known as hybrid or fusion imaging. Tissue Doppler imaging is often used now in cardiography, and it displays tissue motion on the image, which gives more information than just typical grayscale imaging. The tissue Doppler information is superimposed on top of the grayscale image and provides increased spatial resolution, or as we like to say, it's more gooder. And that, after 2 hours and 45 minutes, ends the talk, and I hope that you find it useful. Thank you for hanging in here. Hope you took a few breaks during it too.